Hello, back for some modern algebra made easy. This is Scott Hader. I got some happy news. I got into grad school, so I'm going to be starting that in the fall. Can't wait. Wish I could start now, but I can't. Alright, so I haven't done one of these in a while. Sorry for that, but I'm really happy to get back into this. This is going to be an awesome lecture, by the way. A really good one. I'm really excited for this one. Got some fun stuff going on. So integral domains. And integral domains can be simply illustrated by the set of integers. It's kind of aesthetic, right? You have to admit. We'll talk a little bit more about that later. So let's do a quick review on rings. Rings, we have two operations. One of the binary operations defined on a ring needs to be abelian, and our ring needs to be a group with that operation. The second qualification is that multiplication, our other binary operation, needs to be associative with our ring. All the elements need to associate with the other elements in our ring. And it also needs to be closed. So our ring needs to be closed under both elements. And the third thing is that left and right distribution laws need to hold. Commutative rings with unity. So a ring is commutative if both operations are commutative. If every element commutes with every element under both operations. It has a unity if it has a multiplicative identity. And we're going to call that 1. And if the multiplicative identity equals the additive identity, then we can say that 1 equals 0. Ha ha ha, because we call 0 the additive identity. Alright, let's keep going though. A ring is a commutative ring with unity, get this, if it's both commutative and has unity. Not groundbreaking stuff. I mean, it's not mind-blowing stuff. It's important stuff, but not so hard to understand. Commutative ring with unity. We need to know what that means though. So alright, fields, units. A unit is a non-zero element with a multiplicative inverse. Division ring is a ring where every non-zero element is a unit. So all the elements are units in a division ring. Non-zero elements. So, and a field is just a commutative division ring. So this all just builds on itself. We need to know what a unit is to understand a division ring. We need to understand what a division ring is to understand what a field is. So it's just a matter of getting the terminology straightened out. We'll give examples of these. Well, we already talked about fields last time, but alright, so integral domains, the topic of this lecture. Zero divisors. We need to know what zero divisors are first. So a zero divisor, we have two non-zero elements, and they multiply to be 0. They multiply to be our additive identity, which we call 0. So for example, in Z6, 2 times 3 is 0, right? So those are zero divisors. Both of them are zero divisors. An integral domain is a commutative ring with unity where the multiplicative identity does not equal the additive identity. That's important. And having no zero divisors. So Z6, that would not be an integral domain because we can't have zero divisors like 2 and 3 in Z6. So for example, the integers, which I posted at the second slide, that is the most basic form for an integral domain. It's like the simplest example. We know that the set of integers is a commutative ring with unity. All the elements are commutative, and 1 is our multiplicative identity. And 1 is not equal to 0, obviously. The multiplicative identity is not equal to the additive identity. So also, no two integers multiply to be 0. So it's an integral domain. Integral domain, the set of integers. Integral meaning integers, domain, set, integral domain. It's so simple once you just understand the name. English, it's a beautiful language. Is Z6 an integral domain? I already spoiled the fun on this one. It's not on the last slide. Also, 4 is a zero divisor. it has an element which it multiplies with to get 0. That's in the set. Z7 is an integral domain, though. No non-zero elements in Z7 multiply to be 0. How could you multiply to be a multiple of 0 if none of your elements have a factor of 0? For instance, Z7, the non-zero elements, 1, 2, 3, 4, 5, and 6, none of those elements have a multiple of 7. So they couldn't multiply together to be any multiple of 7. No matter how many times you multiply them, they will never have a multiple of 7. It's kind of interesting. So Z7 is an integral domain. This stuff is so cool. Alright, so here's a illustration which kind of ripped off from the book. It's I still listed the works cited and everything like that. I got it from the text. You can check it out. And I just added some color. We have commutative rings with unity, and some overlap. But not all commutative rings with unity are integral domains, and not all integral domains are fields. However, you can go the opposite direction. All fields are integral domains. All integral domains are commutative rings with unity. Thus, are commutative rings and have unity. I drew it in green kind of on purpose, because I was thinking, okay, we understand what the term integral domain means, but a field is kind of a ring with the richest structure, kind of like a field. And that's why I kind of drew it in green here. It's like the darkest green, the richest field. I don't know. Maybe I'm kind of reaching a bit, or maybe you like it. I don't know. Anyway, it's what I put. So every field is an integral domain. We're going to do a proof. So first we need to know what a field is. We talked about that. Just reiterating again and again until you get it through your skull. A field is a commutative division ring. Division ring is a ring where every non-zero element is a unit. So in this ring we're talking about, okay, so one important thing to look at is the definition of a division ring. For a division ring, we have a multiplicative identity, and it's not equal to the additive identity. So that's an important thing about division rings as well. That to qualify as a division ring, that needs to hold. So let's say we have a field. We need to show that it's an integral domain. Well, all we really need to show is that there's no zero divisors, because we know a field's commutative, and we know that it has a unity. It has unity that's not equal to 0. So we just need to show that there's no zero divisors. To show that there's no zero divisors, we need to show that no two non-zero elements multiply to be 0. In other words, if two elements in our set multiply to be 0, one of them must be 0. They can't both be 0, one of them must be 0. Same kind of logic. So let's take two elements in our field, and let's suppose that, oh, okay, I thought there was something in the middle that was supposed to be here. No. Alright, so let's take a non-zero element A, and we're also supposing that there's another element B, which we already set here, and let's suppose that A times B equals 0. Since we have a field, every element has an inverse. Every non-zero element has an inverse. So A has an inverse. So we just simply multiply by A inverse on both sides, and we see that B must be 0. So if A is not 0, then B must be 0. This means that there's no zero divisors, because one of them must be 0. They can't both be non-zero. So F has no zero divisors and is thus an integral domain. Big check mark. Let's see what we got next. Smallest possible rings. Alright, so this is just a little trivia that I was just kind of thinking about. So smallest possible ring is a zero ring. It's got to have the additive identity. And that's all it needs. It's also a commutative ring, because 0 times 0 is 0 times 0. And it also has unity. It doesn't have a unity that's separate from the additive identity. Yeah, right. But it does have unity, because 0 times any element is that element, because 0 times 0 is still 0. So it does have unity. It's a commutative ring with unity. That would be one of the, when I was showing on the picture, the dark green, the lighter green, and the lighter green, it would be the lightest green. It's a commutative ring with unity, but it's not an integral domain. To have an integral domain, you need a multiplicative identity that's not equal to the additive identity. So you need at least 2 elements. So this would be the smallest possible integral domain, which is also a field. Every non-zero element has an inverse, right? 1 is its own inverse. Alrighty, wow, that did not work out like I was hoping it would. Oh, and there's some Skype information. That's fun. Okay, yeah, gonna have to do this video over again. Or not. Maybe I'll just leave it. Alright, so, I don't know, will you guys forgive me if I just post this? I'm gonna just block out that guy's name. Alright, find the solutions to a polynomial equation, x to the third minus 2x squared minus 3x equals 0. But this time we're in Z12. We're not in the real numbers like we normally are in algebra. In like college algebra or something. So, but now this is a ring. Z12 is a ring. So our left and right distribution laws hold, which means we can factor this equation. And factoring, we quickly find 3 solutions. 0, 3, and 11, which is the same thing as -1 in Z12. So to find the other, since I already have these zeros here, I'm just going to go ahead and spill it. So the other elements in Z12, when we plug in for x, we get 0 when we plug in 5, 8, and 9. When x is 5, 8, or 9, we have a product, which is 0 mod 12. We get a multiple of 12. The others we don't. So we have 3 elements here, and 3 elements here. So that's a total of 6 answers. So Z12 has 12 elements, half of which are solutions to this polynomial equation, which is kind of cool. So it's not like in regular college algebra where we have a maximum of 3 possible solutions. There could be more. So that's that example. Let's do some true or false. True or false? NZ, where n is some integer, has 0 divisors if n is not prime. What do you think? By the way, if you want to think about this, just pause the video. I'm going to show the answer immediately. The answer is false, because, for instance, the multiples of 4, like -4, 0, 4, 8, 12, and so forth. There's no 0 divisors. None of those elements multiply to be 0. Now, if we were talking z mod n, now that would have 0 divisors, right? Z sub n or z subscript n, which we've done several times, that would have, like we did z sub 6 earlier, that has 0 divisors 2 and 3. So that would be a true statement. Next one, a divisor of 0 in a commutative ring with unity can have no multiplicative inverse. This one takes a little bit of understanding the terms a bit and doing a tiny bit of algebra, but it's not that difficult. So let's first of all, it's true. Now let's look at a little proof. If we have we're showing that there can be a divisor of 0 and a commutative ring with unity can have no multiplicative inverse. So let's take a divisor of 0. Let's say A is a divisor of 0. Well, there's something it multiplies with to get to 0 if it's a 0 divisor. And let's suppose that it did have a multiplicative inverse. Okay, then you just simply multiply on the left by the A inverse, and you end up with B equals 0. But B can't be 0. Otherwise, this equation doesn't work as a zero divisor. It doesn't qualify. Like, for A and B to be zero divisors, they both need to be non-zero. Okay? So if B is 0, that contradicts the fact that B needs to be 0 in order for A to be a zero divisor. So if we have a zero divisor, A, it cannot have a multiplicative inverse, which is kind of cool. NZ is a subdomain of the integers. Well, it's using the term subdomain. It's kind of joining two words, subring and integral domain. So is NZ, what do you think? Is NZ, like the multiples of Z as rings, would that be, it is a subring, but is it an integral domain? And it's not, because they don't have the multiplicative identity, right? Like the set 4Z, it doesn't have the multiplicative identity. So it's not an integral domain. The set of integers, is a set of integers a subfield of the rationals? Well, we know that the integers is a subring of the rationals, but in order to be a subfield, it needs to be a field. And the integers don't have a multiplicative inverse for every element, for every non-zero element, so it's not a field. So it can't be a subfield. So those are some true or false. And let's do our proof time. First proof time, an element of a ring R is an idempotent if when you square it, you get the original element. Show that a division ring has exactly two idempotent elements. So there's two elements that when you square it, you get 0. For instance, what do you think they're going to be? 0 and 1, right? That's the idea. Now let's prove it. So we have our ring, R, and it's going to be a division ring. And we're going to have an element in R. Now let's say that I thought this was easiest if we just take two cases. Two cases, this is going to make it really easy. Either let A be 0 or let it not be 0. It either has to be 0 or not 0, right? So let's say A is the additive identity, 0. Well, then 0 times 0 is 0, so it is an idempotent. So that's for sure one of our idempotents, right? Now let's suppose it's not 0. And let's suppose that A squared equals A. Well, non-zero elements in a division ring have multiplicative inverses. So we just multiply by that multiplicative inverse, and we find that A must be 1. Now this only shows that if there is a non-zero element that's an idempotent, then it must be 1. We also need to show that 1 times 1 is in fact 1, that it is an idempotent. It's kind of like uniqueness and existence, which is kind of cool. Don't forget this detail. That's what math's about. Alright, so to wrap this proof time 1 up, since 0 and 1 are idempotents, and these are the only possible idempotents, a division ring contains exactly 2 idempotents. It's kind of cool. Kind of cool. I forgot my check mark on that one. What's wrong with me? Proof time 2. Show that a finite ring R with unity not equal to 0, no zero divisors, is a division ring. This one, please, if you're using the same book as I'm using, please look at the theorem. It says theorem section 5.2. It's a section in integral domains, and it says that every finite integral domain is a field. Please read that theorem. It's really helpful. Even if you don't get it at first, stare at it for a while. It's really helpful, I think. I like it. So let's look at our set. We have 0, we have 1, and we have some other number of elements, some other finite number of elements. And let's forget about 0 for a second, and let's consider the multiples of the non-zero elements, of the multiples of A. So in other words, we're going to multiply each element by a. There's a theorem in that section that says that if we don't have any zero divisors in our ring, then the left and right cancellation laws hold. Different than the left and right distribution laws, right? Two different things. So we can use this theorem to show that if we have any two of these elements that are equal, then that must mean that the element which it's multiplying by must be equal, which is a contradiction because these are all separate elements. 0, 1, a sub 1, a sub 2, all the way to a sub n. These are all different elements. So if we multiply a by them, all of these will be different elements. So the point is that this set right here equals this set right here for getting 0. Because we just do the left and right cancellation law. We just, cancel the a's out on the left. So that means that one of these multiples right here will be 1, will equal 1. 1 and exactly 1 of these multiples will equal 1. So we know that a has a left inverse, or rather a right inverse, because we're multiplying these elements on the right of a to show that one of them will equal 1. And we can use the exact same argument to show that it has a left inverse. So I hope that makes sense. It may require a bit of staring, a bit of reviewing, but I'm confident that it will make 100% sense eventually to you. Oh great, my check mark is first. Gosh dang it. Alright, so let's continue. So in the problem it gave a hint to us. It showed that we not only need to show that it has a left and right inverse, but in fact that those two are the exact same element. The left inverse has to be equal to the right inverse. Those two cannot be equal. Otherwise, it's not an inverse. So let's say, our left inverse, a sub l times a equals 1, and our right inverse, we multiply on the right of a to equal 1. So we need to show that these two elements are the same. So we're going to be crafty. We're going to start out with a sub l. Now, you can multiply a sub l times 1, and that's still a sub l, right? These two are equal. But now 1 is a times a sub r. And since we have a ring, rings are associative under multiplication. So we can use our associative property to go from here to here. But now a sub l times a, that's 1. And 1 times anything is that anything. So a sub l equals a sub r. And now we deserve our check mark. So a, which was a non-zero element in our ring, has an inverse. Which means that a is a unit. And since a is just a general element in our ring, then our ring is a division ring. Because after all, a division ring means every non-zero element must be units. Check mark. That's all for today. Thanks for watching. I'm trying to find a way to upload my notes, my slides as PDFs. If you can think of any ideas on how to do that, please shoot me a message or leave a comment. Anything else, just please let me know. I'm really enjoying making these videos more and more. Hopefully I'll have more time to make them. See you next time.